Hey everyone, hello. It's great to be here with you all. I'm Steve Diamond. I'm with EPA's Office of Research and Development, and I'm a Superfund Technology Liaison. And we do technical support, applied research in Superfund and waste programs, and there are one of us in each of the 10 EPA regions supporting a variety of these types of projects. You may recall I had the pleasure of actually coming to Taiwan in 2014 and participating in a workshop at the time on incremental soil sampling and the use of X-ray fluorescence with my colleague Dina Crumbling. And at the time, I actually gave I think it was about a 1-hour presentation on some things we were working on at the time, and that was high resolution site characterization. Fast forward, here we are, 5-6 years later, and we are presenting a series on, in this case, high resolution site characterization. So, of course, it would be wonderful to be with you and be able to visit and interact with folks in Taiwan, but obviously due to the COVID-19 pandemic situation, we've been forced into a virtual platform. But we're excited to share a lot of these high resolution site characterization concepts, tools, and strategies, and continue what I see as a very valuable exchange between US EPA, Taiwan EPA, and regulators from a number of countries who participate in these workshops, academics, consultants, and others who work on these types of sites. So, and I've entitled this initial presentation, A Practitioner's Guide to the Evolution of High Resolution Site Characterization, in part because to some extent, I've been there through, I've been working on these issues through much of the development of these concepts and the evolution of these concepts. Through Triad, for example, in the late 1990s and early 2000s, working on field-based measurement technologies and real-time analytics, through the early days, and now as an analytical chemist in the early 1990s, as a consultant going into 2000 and 2005, and since 2005 I've been working with EPA on these types of applications of these types of sites. So a little bit of historical perspective here. I've actually taken my picture off because I want to show some examples of particle size effects and some of the challenges that we have. But from a historical perspective, in the soil arena, we've typically focused on high quality analytical samples collected at discrete soil locations and with ultimately a small sample size or a small sample mass. In this case, our typical metals analyses in a laboratory analysis is on the order of 1 or 2 grams. That's about the size of 1 or 2 grams of soil, about the size of a US coin or a penny, yet we often make decisions that are on the order of acres or cubic yards or much, much larger volumes of soil that we are making decisions on. And the particle size effects can be quite dramatic. In fact, here's an example of just a jar that we placed a soil sample in the jar and jiggled it down in a car, jiggled down the road for about 30 minutes to show that just what moving an unhomogenized soil sample in a truck can do to particle size. And you see that all the fine particle size particles, for example, fall to the bottom of this. And if you're in an analytical lab and you happen to take your gram of soil off the top, the metals analyses will be very different for those particle sizes than the ones that you might find at the bottom of the jar. Similarly, in groundwater, we've had the opposite problem where we've historically used long screen monitoring wells, large aquifer pump tests to characterize and monitor our sites. And the subsurface typically looks like this example over here on the left, which is just a cut from a gravel pit, but you can see a tremendous changes in variability in things like grain size and soil type, and all of those are particularly in the horizontal and vertical, and those lead to tremendous changes in things like porosity and hydraulic conductivity, hydraulic head, capillary, even changes in capillary pore pressure and geochemistry lead to changes in how contaminants behave in the subsurface. So the challenges that we are encountered, of course, are using those discrete soil sampling. We can address a lot of the variability and heterogeneity that we find in our soil sampling, and that can lead to highly variable or statistically uncertain decision making, which we want to get away from. On the opposite side, the large-scale averages that we traditionally have received from some of our more traditional characterization techniques, long screen wells, large pump tests, etc., those can obscure primary contaminant transport zones where we're looking at high transport zones, high K zones, and also mass storage, often in lower permeability or low K units, right? So the new thinking is let's apply incremental and composite techniques to help us address the large-scale heterogeneity and matrix variability that we see. And those are better suited to represent our exposure scenarios, oftentimes in things like surface soil exposure scenarios, and help us make statistically confident decisions. And in groundwater, we're finding that if we can move away from the large-scale averages and use high-resolution site characterization techniques, that when we get measurements that are more scale appropriate, that we can tailor our groundwater remediation to help us address those challenges. So what have trends in remediation led us to think about some of these high-resolution site characterization tools? From a historical perspective in Superfund, I think if you look at a lot of our technologies early on, a lot of pump and treat systems. Restoration was often the goal, meaning that we have to achieve a single concentration throughout the aquifer, and that can be quite challenging. And many of the challenges we encountered in the early days were insufficient characterization, which can lead to poor placement of things like well screens, missed sources. We didn't have a great understanding of the challenges presented to us by some of the matrix diffusion issues, and limited flexibility to use our adaptive techniques, right? Our new thinking, of course, can we use a conceptual site model to drive and improve our remedy performance, and can we use high-resolution site characterization and adaptive management approaches in the later stages of the processes where we're actually remediating sites to address that? And up in the upper right-hand corner there, just an example, but every, I think, 3 to 5 years, Superfund puts out a remedy review report. This is the 16th edition from 2020, but it's important for us to gain some perspective on all the types of technologies being applied at Superfund sites. And indeed, if we were to look at that from the 16th edition, a couple of things, just 2 lines I want you to pay attention to here. The red line, which represents our pump and treat technologies applied and for our record of decisions for groundwater remedies. This extends from 1982 all the way through 2017. And you can see that over time, for example, our pump and treats in groundwater tended to be the de facto remedy at 80, 90, even 100% of our groundwater remedies in the early days, down to, by 2017, about 20% of our remedies are now pump and treat technologies, while at the same time, if you look at this dark blue line, which represents our in situ treatment technologies, you see very few, for example, being applied to groundwater in the early in the 80s. As we start to get into the 1990s, things creep up, and by the time we're into 2017, for example, more than 50% of our groundwater remedies actually are applying in situ treatment technologies. So the triad approach historically has been the basis from which we draw many of our BMPs, our best management practices, including elements of high-resolution site characterization that lead to sort of the tools and strategies that we find ourselves employing today. And the triad, of course, came about because there was really an explosion of rapid technology advancements in the 1990s. We had the Navy doing the SCAPS platform, the site characterization and penetrometer system. We had people working on laser-induced fluorescence tools, and membrane interface was becoming commercially available. All of these things were rapidly changing in the late 1990s and into by the early 2000s, for example, EPA had formally developed the triad concept, and by 2005 we actually had a community of practice that was working on all of these elements. But the triad approach really has been sort of the basis of what we've drawn on to help us develop a lot of our high-resolution site characterization efforts. In terms of best management practices, what are they? They're really just a set of methods or techniques found to be most effective and practical means of achieving an objective while making optimum use of your resources. So getting the most bang for your buck, we find that we can pull many of those and identify many of those best management practices through our triad efforts. Of course, the 3 legs of triad be all about managing uncertainty, the 3 legs being systematic planning, dynamic work strategies, and real-time measurement technologies. which is really sort of a synthesis of lessons learned and successful projects that we were looking at in the late 90s and early 2000s. Of course, systematic planning we define as a process for building a consensus vision for conducting environmental investigation and remediation. This is really using your conceptual site model, pulling together your expertise, your project teams, and building a consensus for how you're going to conduct your investigation, understand your knowns and unknowns, and then ultimately remediate the site. Of course, all of this can be facilitated by the other two legs, the real-time measurement technologies and the dynamic work strategies. So for dynamic work strategies, these are really just strategies that incorporate some flexibility and allow us to adapt into information that we generate in the field, and that is often with our real-time measurement technologies. But don't think of the real-time measurement technologies as, only technologies that provide information in, seconds or nanoseconds. We have lots of examples where it's really within time. So if it's within time for you to react to the information in the field and guide a dynamic work strategy, it's a real-time measurement technology. So. I mentioned the rapid advancement of the tools in the 90s, but that has continued obviously through 2000s and even up till today. And those high-resolution site characterization tools have had a profound effect on our conceptual site models and really our understanding of the behavior of contaminants in the subsurface, the distribution of contaminants and the behavior, the fate and transport of those contaminants in the subsurface. And Ben's going to talk about some of the tools here that we typically would employ at our high-resolution site characterization sites. But here's just some examples. In the upper left, this is just a depiction of what the membrane interface probe is. It uses a carrier gas and a heater block. You have the heat, the subsurface heated to about 120 degrees C. Gases will volatilize across a membrane, be picked up by a carrier gas, carried to the surface, and they can be looked at by a series of chlorinated and other detectors, flame ionization detector, photoionization detector, halogen-specific detector, electron capture detector. There's many, and those technologies are improving all the time. At the same time, the hydraulic profiling tool has come online. Basically, you're pushing a small amount of water into the formation and you're looking at the flow and pressures of those characteristics. And when you have a spike up in pressure and a decrease in flow, for example, you're moving into a low permeability unit. The opposite would be the case where all of a sudden your flow is going way up and your pressures are going down. You're into a much higher K unit or a higher hydraulic conductivity unit, perhaps a sand or a gravel. And we can use those tool responses to understand and map out the subsurface. Another tool here, laser-induced fluorescence, has been a tool. We'll talk a little bit, show you some examples from Wyckoff, but it's been a tool that we've done a lot with. It helps us map out petroleum hydrocarbons. Here's the CPT, the cone penetrometer rig, which can push a variety of tools for us, and even some of our profiling systems that provide, that can do several things for us. They can provide stratigraphic information, sample depth selection. This is from the Waterloo Profiler. You can put together a series of these stratigraphic interpretations, which are basically doing what the hydraulic profiling tool is, pushing water into the formation and looking at those flow and pressure characteristics. And we can actually use those in transects, for example, to help us map out. And the nice thing about a tool like this is you can map out the subsurface with all of that, but you can also stop and target specific zones. And this is a good example of things that we often miss with our lower resolution characterization. At this particular site, we have two very high concentrations. What you're looking at here in the brown is sands, and these large white kickovers to the left are actually clay units, represented here in lower hydraulic conductivity units. And most of your mass is in the lower sand units, or most of your where you would see a lot of that mass is in the lower sand units, but it's actually these two very fine sand layers, about 6 inches or less, that has huge concentrations, orders of magnitude higher than elsewhere, and those are embedded within a larger clay unit. Typically, we would not identify those and screen a well, for example, to identify those. But within those finer sand units in a much larger clay unit, for example, you can have concentrations moving at many orders of magnitude above what you might see in the sands just a few feet away. So I really can't stress this enough, but all of these tools, of course, have led to a much more robust and powerful conceptual site model tool set for us as well. And the evolution of conceptual site models over this time frame has been significant as well. In fact, if we go back and look at some of the representations from our guidance here on the left, this is a pathway receptor network diagram that we showed in our 1985 RIFS guidance as an example CSM. And for many years, this was when we asked people at sites, can we see your conceptual site model? We were handed, if we were lucky, we were handed a pathway receptor network diagram. But it's a little too simplistic to serve all of the functions that we'd like conceptual site models to do. And of course, our computing power, for example, has significantly improved with time as well. So we're moving from pathway receptor network diagrams and pretty simplistic diagrams to help us understand our conceptual site models to some of the stuff we started to do in the early 2000s in our triad work. It's a little more cartoonish, but nonetheless, we're documenting locations of contamination, geology, wells, well screens, really starting to understand some of that. And then as we move into 2010, for example, computing power has gone up many orders of magnitude over any other technology. So our visualization and our modeling tools have also have significantly improved, and since about the 2010 timeframe, we've been using those types of tools. This is the Newmark site in Region 9, a very deep groundwater plume. We're able to use some of the visualization tools to help us understand time to restore the aquifer. I'll talk a little bit about the Wyckoff site, but we can depict things like geology and NAPL distribution. And this one here, just showing all of our tool pushes, for example, on a tool like Targos, which is a laser-induced fluorescence tool. So we can really start to visualize and understand and conceptualize much greater and more dense data sets than traditionally we could, where things were buried in a report and it was very difficult to try to convey all of that information. So we went ahead in the 2011-ish, I think, time frame it was, and actually developed a document here that documents the conceptual model life cycle. And we even went so far as to look at how that conceptual site model life cycle would apply to different programs in the US. So here are the elements of the conceptual site model life cycle that we thought were most important. These are the preliminary conceptual site model, often something that you're building to go to systematic planning with. You might come out of systematic planning, for example, with the baseline conceptual site model, some understanding of the parties of what you know, what you don't know, and what you might need to understand better. Moving into a rapid evolution of the CSM in the characterization stage, changes in the design stage, the remediation mitigation stage, and ultimately documenting post-remedy completion and closure of sites. And these conceptual site models become decreasingly conceptual and increasingly quantitative as we move through this process. And it really doesn't matter if you're in CERCLA or Superfund or RCRA. The terminology is very similar, and the processes are all very similar, where we can use our best management practices like systematic planning, like dynamic work strategies and real-time measurement technologies. Most of those have a place throughout the life cycle of those projects as well. So we really wanted to push this evolution of and using the conceptual site model as more of a technical tool for the technical team, but also a communication and management tool to help us address some of these sites.
So here we have the Wyckoff Eagle Harbor site located in Region 10, EPA Region 10. It's on the Bainbridge Island, just to the west of Puget Sound and the city of Seattle in Washington State. It's a former wood treater. It's about 8 acres in size. Currently there's a sheet pile wall that extends around the site, and there is a water treatment facility and the remnants of what was a thermal treatment pilot. We came in 2012 to 14 to add a bunch of Targos to see if we could refine the distribution of the NAPL at the site. But here we're looking at the geology, and typically how we build the geology. We have an aquitard here, We've placed a vertical exaggeration of 3:1 onto it, and we've taken about 80 existing logs from the site, classified those logs, and used those to build essentially a geologic representation using EVS, Earth Visualization Software, or MVS, Mining Visualization Software. And we've taken all of these well logs, and essentially we can look at, we can do some geostatistics and kriging and look at the distribution of grain size. So here we're looking at higher hydraulic conductivity areas in blue. You can think of these as your sands and gravels, and lower hydraulic conductivity units in yellow and red. You can think of those as your silts and clays. And in fact, here we've turned off the high hydraulic conductivity units, and we can look at the distribution of the silts and clays at the site, and that becomes important when we look at where the mass is stored and also where some of the mass is moving as well. And we can look at it a variety of ways. Here we've turned off the low hydraulic conductivity units, and we've included higher hydraulic conductivity units, particularly on this side of the site. And down close to the sheet pile wall as well, there are some gravels and other things. And of course we can do block diagrams and other ways to look at the distribution of grain size across the site with depth and slices across the site. So now we have the Wyckoff site, and we've placed on the distribution of NAPL material that the Targos tool, about 180 to 200 pushes of the Targos tool throughout the site and outside the sheet pile wall. That's the integration of all of that data, and also we're showing some historical operations here on the surface. For example, this was a dock where they floated the logs in to do the treatment, and these yellow areas that you see are actually historical excavations that have been brought up to the surface. So if you look at the NAPL distribution directly under those yellow cylinders or boxes, for example, you'll see that there isn't much distribution of NAPL. And that's the result of the excavations that were done in some of the early days of the project. So if you look directly under that yellow block, for example, you'll see that there isn't. But what we've done is we've used the geostatistics and the kriging, and we're looking at everything that the Targos tool produced with a signal greater than 10% of the reference emitter. That is typically how they provide a response for that tool, and gives you an estimate of sort of how much NAPL might be there, but really it's the distribution that we were after, and we were able to obtain that at a very high resolution with those Targos pushes. So here you're looking at the NAPL distribution, or anything that gave us a greater than 10% RE signal for the site, and really high resolution look at the distribution. It's not the full 8 acres and the $200 million thermal remedy that we thought, which leads us to the last visualization that I like to show, where we can use some of this to actually help us with our remedial designs. Now here we are, and finally, after understanding and visualizing the geology and the distribution of NAPL, we undertook an exercise to see if we could, quote, compartmentalize the site into different areas where specific treatment technologies make sense. And in particular, some of the treatment technologies that we had in mind based on the grain size distribution and based on the distribution of the NAPL were in situ stabilization, chemical oxidation, some sparging, and other techniques, bioremediation, because really what's driving the risks on the site are the dissolution of the NAPL materials into water and then going into either the Puget Sound or impacting groundwater. Those are the major issues. So what we've done is basically assigned a bunch of treatment boxes to different areas of the site, and we were able to capture most of the NAPL in those treatment boxes. And so this is a way that folks can get an estimate of the volume of the material that might need to be treated, different technologies that might apply. So stabilization in the orange box, stabilization in the perhaps in the yellow and blue boxes. There's opportunities to do some things with some of the lighter materials, for example. In this light blue box over here, this would be the area focused on for chemical oxidation. This material tends to have an LNAPL or a lighter signature than some of the materials that you would find, for example, over here along the aquitard, which tend to have a much more of a DNAPL signature. So it's a complex mix of TPH that's been spilled and moved around and transported across the site over the 100+ year history. And we were able to come back in with this technique to try to see if we could visualize all of the different distribution of the NAPL and look at technologies and volumes of material that we might need to treat with those technologies to understand costs. And to give you some perspective, I think the high resolution site characterization effort and the visualization cost several $100,000, maybe on the order of $400,000 or $500,000 US. But the current remedy estimates and what they're applying at the site are about on the order of $100 to $130 million. So we're looking at a reduction in a $200 million estimate thermal remedy to a combined technology remedy on the order of $100 to $130 million being applied today.
One of the ways that we've recognized the need for high-resolution site characterization tools and strategies has been through some of the realizations that EPA Superfund has had in the optimization program. The optimization program, which was started in the late 1990s, the first recorded optimization was 1997 under Dan Powell's group in Superfund with Kathleen Yeager, and looking at some of our long-term monitoring optimization networks to look for opportunities to try to improve our monitoring networks, and looking at a lot of our pump and treat systems, which were in long-term operation and maintenance. Of course, by the 2000s, EPA was working closely with the Army Corps of Engineers, the U.S. Air Force, and others, collaborating, and those results and those collaborations resulted in refinements of tools and standardizations to optimization processes in those various programs. At the same time, the Interstate Technology Regulatory Council, which is a group of state regulators, academics, and others, put together a series of guidelines on performing optimization. And by then also EPA had a web presence and had performed more than 100+ optimization events in the Superfund program itself. We continue to look for opportunities to improve the performance of our remediation systems and the performance of our systems by looking at them in the remediation stage and moving further up the pipeline, looking at some of our sites as we were developing designs for those remediation systems and using the optimization program to look for opportunities to improve at those. And then finally by 2010 and later, actually looking at sites in the characterization stage to look for, or investigation efforts to look for opportunities to improve the conceptual site model as a means to implement optimization earlier and earlier in the pipeline. In fact, by 2010, the OSWR, the Office of Solid Waste Emergency Response Assistant Administrator, noticed the successes that the Superfund program was having with optimization and requested the development of a national strategy. And by 2012, EPA released a national strategy to expand Superfund optimization from site assessment to site completion. And today in the Superfund program, obviously, we fully implement optimization. Of course, anywhere along that process, you can include triad approach best management practices and green remediation, some of the best practices that go with our green remediation evaluation efforts. And in terms of what is optimization, well, the optimization, EPA Superfund defines optimization as a systematic site review by a team of independent experts, technical experts, at any phase of the cleanup process to identify opportunities to improve remedy protectiveness, effectiveness, and cost efficiency, and to facilitate progress towards site completion. Now that's a big mouthful, but basically we're looking for opportunities to improve our remedy protectiveness, the effectiveness of those technologies, and the cost efficiencies by which we drive those programs. So there's a lot of information on optimization and Superfund optimization, particularly on various websites, but just to look at sort of what the process is. Basically, we get a team together, we have a scoping call, exchange documents, sometimes there's site visits, and ultimately what comes out of it is a series of recommendations, and then we track those recommendations for improvements to the remedies. Just an example, this is from the 1997 to 2016 timeframe, but Superfund typically rolls up these events and looks at a lot of the recommendations. And one of the interesting findings for me is that whether we look at sites in the characterization phase, the design phase, or even the long-term operation and maintenance of our remedies, oftentimes our findings are similar in that we have needs for conceptual site models or additional characterization. In fact, there was a time in the 2000 timeframe when we rolled up some of the early optimization events and looked at all of the recommendations and found that more than 50% of the recommendations were for improvements to characterization, improvements or development of the conceptual site model to help us navigate through these other phases. So typically the findings in characterization: low data density, an underdeveloped or out-of-date conceptual site model, over-reliance on low-density, high-cost methods, not considering scale-appropriate measurements that we get from some of our high-resolution tools. When we move into design, gaps in the conceptual site model, high-cost estimates resulting from a lot of variability and gaps in the CSM. And similarly, conceptual site models need update as we move into the later phases and we're having an effect on the contaminant plumes and distribution. We need to understand where are our sources, where are our transport and storage zones, do we have things like NAPL on site, etc. And many of our optimization findings point to those as needs even later in some of the phases of the Superfund pipeline. So it is precisely those challenges that we find through optimization with our pump and treat systems and a variety of the technologies that we now apply, that the challenges remain for us in groundwater. And historically, when going back to the 80s and 90s, for example, many of our conceptual site models thought that we lived in a homogeneous, isotropic aquifer conditions where it doesn't matter where this is homogeneous and isotropic. So no matter where you move within the box or the direction that you move in the box, the changes are of the same magnitude. When really most of the aquifers that we're living in are this one down here, anisotropic and highly heterogeneous, meaning it's going to vary. Properties like hydraulic conductivity are going to vary when you move in the vertical versus the horizontal, and also as you move around different places within the matrix itself. And that is very different from some of our early on conceptual models of how plumes behaved. In the early days, for example, many of the researchers thought that dispersion was a major factor, and that many of our plumes came out and were shaped in these large fan-shaped plumes driven by dispersion. But what work that they did at the University of Waterloo, the Cape Cod tracer tests, and some of these others showed that actually dispersion transverse horizontal to the direction of the plume is quite weak. So the plumes don't necessarily, under the influence of any other force, spread out through dispersion into these large shaped plumes, but actually, like the research from this example in the University of Waterloo showed, that they can maintain these very long and thin shape, these plumes, long, thin shaped, cigar shaped plumes, and that actually dispersion along the axis of the plume can be significant, so that you can see larger dispersions in the concentration gradients, for example. But when you move to the side of that, in the absence of forces pumping and other things acting on it, those concentration gradients are quite steep, and that the plumes are quite long and narrow versus the traditional larger fan-shaped plume that some of our early conceptual site models thought about. And of course, we also have the phase to think about. What is the contaminant phase? Is it are we chasing it as a NAPL? Is it in the gas phase? Is it dissolved? Or do we have problems with sorbed onto the matrix? Because all of those affect the types of technologies that we then might apply, as well as the tools that we would search for those contaminants with. So this is a good example. Some of the early work that we did with the high resolution site characterization course I did with Seth Pitkin. Seth was a student of John Cherry at the University of Waterloo and also was involved in development of the Waterloo profiling system. And Seth provided a number of pictures and stories about early days of trying to understand how some of these high resolution site characterization tools were operating. So here's an example of a site in Canada that Seth worked on, where at the time he's working on the development of the new hydraulic profile, the Waterloo profiling tool, which is able to grab a series of very small discrete samples. And we can look at the distribution of the concentration, in this case, of PCE. And at the time, and this is the case in many states and regulatory programs, to prove that your tool is working, you have to compare it to some accepted regulatory method. So at the time, Seth was trying to compare the concentrations that he was obtaining at these discrete sample locations with a well. So he has a pretty high density distribution of discrete sampling locations and the concentrations of each. And then, of course, he went back in and dropped a well screen across this high contamination zone that we find here. But the concentration in the well was on the order of about 2,000 micrograms per liter of PCE. Yet within that well screen, or within that zone, he could have concentrations on the order of 20 or 30,000 micrograms per liter of PCE. So how can that be? As Seth questioned himself, was the tool creating mass? Well, of course not. So what the tool provides is a measure of hydraulic conductivity. And what you see in many of these wells, and why some of my colleagues over the years have joked that monitoring wells are holes in the ground that lie, not necessarily true, but you need to be very careful in understanding the type of data and information that you're getting from a monitoring well, particularly long screen wells and what that can do. So here's an example of, in this case, we have very high concentrations that happen to be in the middle of the well screen where the lowest hydraulic conductivity measurements are obtained. And at the top and bottom of the well screen, you have much higher hydraulic conductivity. So what you get in this well screen is what we call a depth integrated flow weighted average. That's a mixing of lower concentration high flow zones with higher concentration low flow zones, and ultimately an integrated depth flow weighted average across that entire well screen. At the same time, we've been thinking about mass flux distribution and mass methods as all of these in situ remedies continue to rise. So here we go with the decreasing trend in our pump and treat applications, and in this case, the green with the clear diamonds are looking at up through 2011, an increase from almost no in situ remedies to about 40% of our groundwater remedies. At the same time, there's research going on in the 2000 timeframe by a gentleman by the name of Martin Gerbeau, and he looked at very high resolution sampling at a PCE site in New Hampshire. And so what we have is a series of transects through the site and then very high resolution vertical sampling. And what his research showed is that something like 75 to 90% of the mass is moving through 5 to 10% of the cross-sectional area. Now think about that. That is profound. What that means is that most of the mass that is moving into and causing us issues with our receptors is moving across a very small cross-sectional area, 5 or 10% of the cross-sectional area. So that if we have high-resolution site characterization tools to identify those zones, those 5 or 10% of the cross-sectional area where most of the mass is moving or being discharged, then those are the areas aided by our high-resolution site characterization tools that we can much better target with targeted in situ remedies. So we know that the flux can be variable in space. That is the distribution of the material in space, but it also varies with time. This is an example of what's called the 14 compartment model generated by Tom Sale at the Colorado State University and Chuck Newell with GSI, but it looks at sort of the early, middle, and late stages of a DNAPL site and what the source zone and plumes look like and where mass might be moving. So for example, in the early stages of a DNAPL plume, most of your mass is probably in a DNAPL form and located in the higher K or more transmissive zones, but it's starting to diffuse into lower permeable units in the aqueous phase, perhaps as a NAPL, and in the vapor phase as well. Excuse me. But at the same time, in the middle stage, what you're finding is that a lot of that mass transfer has taken place. This is the middle stage, the life cycle of the plume, if you will, that now you're finding NAPL in the transmissive zones and in the low permeability units. And by the time we get to the later stages of the life cycle of a DNAPL site, what you find is that most of the stuff in your source zone is probably trapped in low permeability units, and that mass is moving down gradient in the plume in the transmissive zones. And here's an example of that exact phenomenon happening. This is a dry cleaner in Massachusetts. But you notice here in the source zone, for example, that where you have your highest PCE concentration, you also have your lowest K value, your lowest hydraulic conductivity. So here in the source zone, high concentrations in our low hydraulic conductivity units, versus when you go down gradient at the same site, your highest hydraulic conductivity or your highest concentrations can be found in your higher K units, your higher hydraulic conductivity units, meaning that mass is moving in the transport zones down here in the down gradient. So here's a very quick and simple case study of an early HRSC site that we looked at. This is using transects and vertical profiling at the Pease Air Force Base in New Hampshire to look at a volatile organic chlorinated solvent plume, also co-located with petroleum oil lubricants. These VOCs were essentially affecting two down gradient bedrock supply wells, one for the city of Portsmouth, New Hampshire, the other for Red Hook Brewery. So now we are worried about the water supply of a town and also the water supply of a brewery. Prior to the monitoring well investigation, the plume was defined as a short plume where they thought it was basically degrading very rapidly and didn't seem to be traveling down gradient to cause a problem with the municipal well or the brewery well. The team came in with a series of transects, 5 transects using the Waterloo profiler. You see them here. This is in the source zone, B to B prime, A to A prime, just down gradient, and then a series of transects moving down the plume. And if we look at the source zone, B to B prime, and just down gradient, immediately within 2 transects, you have some understanding of what the plume is doing, and it's diving. So here we have higher concentrations located closer to the surface in the source zone, and as you move down to the second transect, just down gradient, you're finding that your plume has started to dive deeper. Now at the same time, we also have a series of wells that were already at the site. This is what the plume ended up looking like post the high-resolution site characterization effort. These wells in black were wells that were there prior to the investigation, and it's quite interesting to see that typically we put wells up gradient. They use multi-level wells to try to find the plume. In this case, the multi-level wells are not doing a good job of defining that plume. And then, of course, a long screen well, which would have challenges like, as I mentioned, with depth integrated flow weighted averaging, where you might think that there's a very low concentration and that the plume is dying out based on that well. So they came back in with a series of transects. You see here at B in the source zone, A, C, D, and E as we move down gradient. And the plume ended up looking like what you see there depicted, the TCE in blue and some of the other breakdown products associated with it. And what you can see from the transects is that indeed the plume is heading down gradient and makes it to bedrock. So they were able to come back in and put appropriately screened and better designed monitoring wells to help monitor the toe of the plume, and ultimately at the site they placed a reactive barrier, and you can drink Red Hook beer today. So lastly, I just want to end with sort of some thoughts about where I think all of this high resolution stuff will continue to go. So as Buzz Lightyear would say, to infinity and beyond. And this is really an expansion, I see, of just a continuation of using the tools and strategies that we've been developing over the years. So that includes in groundwater using things like transects, very high resolution vertical profiling. A lot of that is aided by our direct push and direct sensing tools. We can facilitate flux-based approaches, which are becoming more and more used, and looking at site investigation through optimization and remedy completion using those same tools. And on the soil side, we can do something very similar, deploying our incremental and compositing designs, looking at depth discrete intervals in consultation with our risk assessors, using our field-based analytical methods to control heterogeneity and particle size effects and improve our risk-based decision making and guide us through that same investigation through remedy optimization. So thanks.